Hey everyone, we're going to start today working our way over to the study of dynamics. Before we were studying kinematics, which was how the motion of things. This is why things move. So dynamics studies how objects move and why. So it's related directly to kinematics. But we're going to extend some ideas underneath it all. And so the first things we're really going to have to do is look at just motion in general. Now, we started with Galileo's idea of relativity. We got relative motion in the end, that when you have an object moving, let's say like a boat, and you're on that boat, and you do some motion, relative to the object moving, that motion is if I'm on the boat and I throw something up, it falls straight back down. In a cabin on a boat, I think is how Galileo said it. And if you're in the cabin on the boat and you throw something up, it goes straight up and it falls back down. But if you're to watch on the shore, you throw it up and it moves with the vector of the boat's motion coming across. And so Galileo started the idea of what's called relativity and relative motion. And Galileo worked out most of the rules that became kinematics that we see. But it took Newton to come around and figure out what was happening. Now Galileo defines the main thing that Newton took, and that is inertia. Something about motion, or an object in motion, it resists a change in its motion. And so inertia is going to be this thing that resists change in motion. Now, from our kinematic equation viewpoint, this means that inertia causes accelerations, or not inertia. Inertia would be the inertial state of an object resists accelerations. This is the best way of saying it. Something about an object resists acceleration. And if we think about, if I put a box on the table and it doesn't want to move, it's not accelerating, and if I push the box, it will start to move after I've pushed it hard enough. If I take a bigger box, I need a bigger push. And so something in the difference of these two things relates to inertia. And what Newton did, and what we are going to use, is we're going to use the concept that mass is a measure of inertia. So an object's mass is a way of telling how much stuff is there. I want to talk a little bit here so to keep this going. An object's mass is a measure of its inertia. And so if we look at like the smaller object, it has less inertia. It's easier for me to accelerate. And if we look at the bigger object here, right, its mass, it's harder for me to put an acceleration on. And we can also think of mass as the amount of stuff, right, on an atomic level or a particle level. And so if we look at these things that we're creating, the amount of stuff present resists motion, resists change in motion. Now Newton really tried to understand the relationship that we're going to have between, our boxes here. There's our boxes. And the interplay between mass and motion. And so Newton's laws are actually a reflection on something with little stuff, something with more stuff. And with the thing with little stuff and the thing with more stuff, how does that react to the kinematic equations we had before? And so the key that we're looking at here is stuff. And I know stuff is not a great technical term, but it's the part we're going to look at. And so what Newton said in his laws was that push or that action that you do, and he actually called it an action, but we're gonna change and call it a force. And so his first law is called the Law of Inertia. And it is really a reflection on what Galileo observed. And it's every object continues in its state of rest or of uniform velocity in a straight line. So my box isn't going to move as long as no net external force acts on it. So let me change colors here. My object can be sitting still. Its acceleration is equal to 0. And I give it an external force and it will start to move. I have an object with an acceleration equal to 0. Oh, well, we'll say velocity is equal to 0. And it has a straight line velocity, and we'll say 1 meter per second. That's also in an inertial state. It's not going to accelerate. If I come and apply a force to it, then my acceleration goes up. In all cases, the application of the force changes the acceleration. So the first law, and what Newton is doing with the first law, is he's recognizing inertia. He's saying that inertially, because of the pointer issues, when I talk, you're going to see me, but I think this is kind of cute. I've got words in front of me. I could write on it, but whoa, volume went up there. That's better. Microphone, and didn't mean to shout there. And so what Newton's recognizing is this principle that Galileo saw, that something with a 0 acceleration and a 0 velocity isn't going to move until something pushes it. And then something that's moving at a constant velocity isn't going to accelerate unless some external force acts on it. Right? So, and this is just an observation, right? Inertia is this thing that we don't, if we're in some type of motion, if I'm doing my straight line motion, I'm not going to want to change unless some external force pushes me or pulls me. Push or pulls will be the words we use. And so we should be noting that the key thing that Newton's noticing here is the acceleration and the force are related. That's the part that Newton really pulls out into his second law. Now, notice this is straight line motion. If I have an object and it's moving like this, but I want it to turn, I have to do an acceleration in the direction I want to turn. So when we have things moving in a circle, they have some type of acceleration to turn in. Because if they didn't have an acceleration inwards, they'd fly straight away. So inertia says you'd fly straight away unless there was some acceleration inwards, which from Newton's idea means there needs to be some force inwards. And we'll explore that more when we study circular motion. But let's look at Newton's second law then. And so Newton's second law is he looked at his first law and he turned it into math. There's nothing big in Newton's second law. And what he said was that, let's see if I have the exact wording of Newton here. He said that the sum of all of the external forces as a vector is equal to the mass, which is a scalar, times the acceleration vector. I think his wording was that the action, which is inversely proportional to the mass over the resultant, I think, because this is the resultant sum. So this is the resultant, this is the action. The force is the resultant. And again, my pointer issues here, so I'll point with my body. In this equation that Newton did here, so this is the resultant, and this is the mass, and then this is the action. The acceleration is the action. That it's a response to the force. And this states, over here, right? This states the principle. Sorry, I'm having the pointer problems, and this is my adaptation to the pointer. I'm not sure I like it yet or not, but we'll play with it. And this equation, F equals ma, is kind of the grounding of Newton's second law. And then in Newton's third law, which is, I guess, the law of symmetry. If I have the force on object 1 is applying to object 2, it is equal in opposite vector direction to the force that object 2 will push on object 1. So forces come in equal opposite pairs. When you push on a book, the book pushes back on you. And these three laws together let us determine all motion. Now, a couple things happen here that the motions we see get some limiting factors. The first is that we're going to all of these laws are only valid in inertial reference frames. And it's a weird recursive definition. We say inertial reference frames are the places where Newton's laws are valid. And what that means is that we can't have things rotating. So our relative frame can't be rotating. And our relative frame can't be accelerating. Well, let's look at these two things. Let's take something rotating and we'll put an object on it. And again, I'm going to want to point at this, so I'm going to do this. Right now, this is my fix for the pointer. I kind of like it and don't at the same time, so we'll see what we can do with it. But so here, I have an object that's rotating. And so I put this object on a rotating turntable. Think of like at the park, the little spinny things you would go on. Now, when you're on a rotation, you want to continue inertially in a straight line direction. So to rotate, you kind of have to lean up against the sides, right? You lean up against the sides, or you put friction on the bottom because you need to push in towards the center. So if you were to, on that rotating thing, throw something in a straight line, if this is your reference frame rotating around here, you're going to see it as curving. And that breaks Newton's first law of the straight line inertial frame. So an inertial reference frame can't be rotating. Now we can also think about, if I come back over here, let me see if I have some room. Nope, I'll do it over here. One that we commonly see is our friend car. All right, that's my wonderful car. All right, so you're in the car and you're going down the road. So we get our car and we're going down the road and we're in it and we start accelerating. So we're going faster. if I were to throw an object up and speed up the car, that object will want to move in its straight line motion. And so as I speed up, the car moves underneath it and it will curve. So within that reference frame, we don't get the straight line motion or the straight line inertia. By having these accelerations, we're going to find when we define rotating things that a rotation is an acceleration. Even if I'm moving at a steady velocity, because my velocity vector in this direction wants to change, a change in a velocity vector is an acceleration. And so non-inertial frames are frames that actually have some type of acceleration, via a rotation or the frame itself is moving. Because if I'm moving like this and I throw my pen up, that's great, the pen comes back down. But if I'm moving like this and I'm going to accelerate, I throw the pen up and accelerate, my local frame of the pen. So if I'm not accelerating, moving straight up and down, the pen goes up and it comes back down to my frame. Now if I'm in an accelerating frame, I throw the pen up and it's going to move backwards and it's no longer in the straight line motion. And so inertial reference frames are frames in which Newton's laws apply, which means the frame itself is not rotating. All right. So these are the laws that we set up, and we look for inertial reference frames. And so mass is the property of the object that defines inertia. All right. I filled out this blackboard. Let me clear it out. So let me come here. I'll clear it. It'll go white because I messed up my settings. I'll make it go to a blackboard again so as not to kill the eyes. Scroll up and get my pen back up. All right, so Newton has set up a mathematical framework for us. And our mathematical framework is the vector quantity of the force is equal to the scalar, how much stuff, the inertial property of the object, times the vector quantity of its acceleration. And this is going to be our main tool. All right. Now, anytime an object exerts a force, another force is equal in opposite direction to it. But the forces are on different objects. So, for example, if I have a wall and I'm on roller skates, do my stick figure me, and I'm going to push on the wall. I'm pushing a force on the wall. I'm having a force on the wall. The wall pushes back on me. So if I were to draw a diagram for the wall gets a force due to me. And we'll find that there's reasons that the forces balance back out. But me, if I do a diagram of me, get my skates out here. And I'm pushing here, the wall pushes back on me. And because my skates are frictionless, I move in that direction. That MA causes an acceleration and my motion is in that direction. In fact, we could calculate the motion if I knew how much my push was. My motion would be proportional to it. That F equals MA. So when we look at this third law interaction, realize that the frictional forces in the wall push back. And so I could say the forces of friction from the wall push back. And when I add these two up, I get zero acceleration. So something about these cancel out. Where here, as the skater, whatever force I applied there is going to equal my acceleration. And so my acceleration will have a magnitude in that direction. So notice the balancing act we did. The sum of forces, if it adds up to 0, I don't move. If it doesn't add up to 0, I move. And that's the key goal to Newton's laws. And so the notation I use, and I think your book might do it backwards, I do the force of the object onto something. So object 1 onto object 2. I think your book might do it the other way around. But again, you just want to be consistent. Make a nomenclature that works for you. For me, it's the force of object 1 on 2. And then if object 2 will push back on object 1, equal in opposite direction. Now remember, a negative sign in a vector is opposite in direction. Right? These are vector quantities, and so a negative vector is in opposite direction. And that's what we're looking for here, is opposite directions. All right, let's look at a force that is common for us. We've been talking about in our free fall, and we've been watching objects fall. They've had an acceleration that was equal to negative 9.8 meters per second squared. So if I take a particular object, let's say a 10 kilogram paperweight, and I subject it to this vector, I can say the force on that paperweight is equal to the mass times the acceleration, or 10 kilograms times negative 9.8 meters per second squared, or negative 98. Let's look at our kilograms, meters per second squared. Well, this we're going to call a Newton. Negative 98 newtons. And a Newton is the SI way of talking about weight. When I talk about something's mass times the acceleration due to gravity, that's what we actually call weight. And so in the metric system, a Newton is the measure of weight. Mass is how much the inertial quantity of an object, and mass times gravity is weight. And so a Newton has units of kilograms, meters per second squared. If we look at it from a dimensional analysis standpoint, it's going to spell out Newton's laws here, right? We have mass, length, times to the negative 2. And so there's Newton's laws in the dimensions that come out in our units. So we always want to make sure our units check. And so we now have a new thing that we've added to our list of things, and that is the Newton. Our journey has been from nothing to displacements in length, right, delta x's, to velocities, which is delta x over delta t, to accelerations, delta x over delta t squared. Sorry, delta v, right? Change in velocity. Sorry about that. And then and now we have mass, length, time negative 2, which is our newtons, or the F equals ma. And so we're building our knowledge of the universe out of these dimensions, working our way up. And again, Newton, notice the relationship between an object's mass and it wanting or not wanting to move. All right, since we're not zooming, I'm going to pause this here. This will be video 1. And this introduces Newton's laws, and we've just now started to look at them mathematically. We have their units, we have how they interact with the units, and we have everything we need to know to start problem solving on them. So what we're going to do is we're going to look at common forces and how to problem solve them.